Hello, ladies and gentlemen. Welcome to Chapter 13, Day 2. Today we're going to look at 2 of 3 experimental designs that we're going to focus on in this class. So just like with sampling, there was different designs that we used, simple, random, stratified, systematic, and cluster. There are certain kinds of experimental designs you need to be aware of. So the first one we're going to look at is basically the completely randomized design, kind of the equivalent of the simple random sample. It's the most basic experimental design that we talk about. And in this design, the experimental units are randomly assigned to treatment groups. And so with the treatments, there can be 2 treatments, there can be 3, there can be 4, there can be 5, there can be 6, there can be as many treatment groups as you want, and then you compare results between the treatment groups. And so where we are right now is just the design of this, and so the comparison is the more mathematical aspect that we're going to get into in January and February. That's where we kind of look at the data and mathematically analyze it. So for right now, you just need to understand, okay, we have all of these experimental units, we're going to randomly assign them to treatment groups, and then we're going to compare the results. Now, in the randomized comparative design, it is imperative that you include what we refer to as a control group. Okay? And this could be a placebo group, or it could be a group that receives nothing. It could be a group that receives a current product when comparing to a new product. And basically, the reason is, or what the control group does, is it acts as a baseline comparison group. Okay, so we can determine whether or not the treatment, the real treatment, is causing a desired effect. All right. So the idea is you need a control group to act as the comparison group. So we can say, okay, let's determine if something works. So think of like the COVID-19 vaccine. If in phase 3 they had 40,000 subjects who said, hey, I want to take part in this, and they give every single person the real vaccine, and then they come out and say, well, the success rate among this group was this, well, then you don't know if that's better than no vaccine at all, because you don't know what would have happened amongst another group. So you need that comparison group to say, okay, the success rate with the vaccine was at 95%, whereas the success rate without the vaccine was only at 60%. Now we can see that this is significantly better. That's why we need that control group to actually determine if something works. Because if you don't have control group, our results can be biased. All right? Meaning that they are systematically favoring a specific outcome. Okay? Because you could, just like you can have bias in sampling and surveys, you can have bias in experiments, the way they are set up. So the idea is to incorporate randomization when assigning your treatment groups, to incorporate a control group, aka a baseline comparison group, so you don't have biased results. All right, so let's go through an example, and we're going to kind of tie in the vocabulary from day 1. A researcher wants to conduct a study to test whether listening to soothing music for 20 minutes helps reduce systolic blood pressure in patients with high blood pressure, compared to simply sitting quietly in a noise-free environment for 20 minutes. 100 patients with high blood pressure at a large medical clinic are available to participate in the study. A. Identify the experimental units. So, who or what are you using to carry out this experiment? Well, you have 100 patients, and now it's important. These people are not randomly selected, okay? In this particular scenario, you need people with high blood pressure. So some people say, well, don't they have to be randomly picked? No, in this situation, it's not about randomly picking people, because you have to have people with high blood pressure. Okay. What is the explanatory variable? Now, this is where it gets a little confusing. So if we actually go to C, you would say, okay, how many treatments are there? Okay, you look at this, say, okay, it looks like there's 2 treatments. There's 20 minutes with soothing music. Is that how it's described? Yes, soothing music. And 20 minutes. I can't spell right now, or it's not writing. Minutes with, how do you describe it? Noise-free environment. Okay. So now, just like kind of way back in chapter 2, when I said when you identify a categorical variable, like if it's male and female, the variable isn't male and female. The variable is gender. If you're talking about politics, you say, well, what's the variable? Democrat, Republican, Independent. I go, no, that's not the variable. Those are the categories of political party. So likewise here, it's the same idea. The treatment groups are 20 minutes in a soothing music environment and 20 minutes in a noise-free environment. So the variable would be kind of what we say environment. So it's kind of links back to chapter 2 where we identify a categorical variable. Nope, we're going to do that. Nope, remind me later. All right, so kind of the same idea. I said we're at a point where things kind of start coming back that showed up earlier in the course. What is the response variable? Okay, helps reduce blood pressure. Let's say, so the reduction in, what are they, diastolic blood pressure. Okay, there it is. Helps reduce systolic blood pressure. And so in this case, this noise-free environment, this would act as your control group. All right? This is not really a placebo. You can't give them fake music, so they would act as the control group, the baseline comparison group. Use a diagram to show/describe a randomized comparative design for this experiment. So for this, we create a very basic diagram. So we have 100 patients. Here's what we do. We have 100 patients. Now the diagram does need to be detailed. Patients with high blood pressure. And for the sake of argument, let's say we're going to split them 50-50. You don't need to split them 50-50. All right? If you're doing random assignment, there's no guarantee that you're going to get 50-50. All right? You might get like 48 and 52. You might get 46 and 54. You might get 45 and 55. All right? So, but for the sake of the diagram, we're going to say, all right, we're going to randomly assign, and we're going to get into how we would maybe do that, 50 to soothing music environment, and we're going to put 50 in 20 minutes, be more specific there, and then 20 minutes of noise-free environment. Okay, so this randomization is key because it says we're going to do this randomly. We'll describe a process in just a second. And then we identify very clearly what the treatments are. And then the final step is to kind of identify your response variable. So we compare changes or reduction in diastolic blood pressure. So really, part A through D here was to really get you set up for this diagram for a randomized comparative design. That was the whole purpose. So all of this in A through D was basically from day one: experimental units, explanatory variable, treatments, response variable. That's all the vocab that was established in day one. And so now we use that to set up a diagram for the comparative design. Now, how could we possibly randomly assign the experimental units to the treatment groups? Well, I'm going to stick with the whole idea of a random digit table, because that's what you're used to. So, assign each person a 3-digit value from 001 to 100. So we're going to omit 101 to 999 and 000. Okay? I'm trying to stay consistent with what was first established back in simulations. That was then carried over into sampling design, and now which carries over into experimental design. So then we're going to select 50 unique 3-digit values between 001 and 500. The 50 names that correspond to the numbers chosen will create the music treatment. Okay, so once again, same idea. Assignment of numbers, selection of numbers, corresponding people to the numbers chosen. Now keep in mind here, we're not randomly assigning numbers. You say, okay, person you, Jim A, you're going to be 001. Sarah B, because your last name begins with a B, you're going to be 002. All right? You purposely assign them numbers. The randomization comes, I forgot to add this, using a random digit table. The randomization comes in when you're selecting the numbers to create a group of 50. And since we're creating a group, we're going to do unique values, which means we're going to skip repeats. The names that correspond to the numbers chosen, they're going to create the music group. Okay? The remaining 50 people create the noise-free treatment group. And there you go. That is how you can randomly assign these 100 patients with high blood pressure. Now, when you are describing, when you're doing this part, all you have to do is provide the diagram. If I want you to describe the randomization, I will specifically ask you that in a follow-up question. But if I just say, hey, show or describe a design, this is what I'm looking for. I'm looking for this diagram. If I want you to specifically say, okay, here's how you would randomly assign them, that would be a separate question, as you see here in part F. All right, how are we doing on time? All right. So the other type of design is a block design. And in a block, so block is kind of like stratified sampling. Very similar. A lot of people get them confused. But stratification is to sampling, and block is to experiments. So a block is a group of experimental units that share a common characteristic that is known to influence the response. Okay? So it's kind of the same idea. You're creating groups that are specifically different than each other. There's something about group A that they all share a common characteristic, and group B all shares a common characteristic. But group A and group B are very different. In an experiment, you would do this because you know that group A might respond differently to the treatment. So in a block design, you add control by isolating the blocking variable. The example will kind of clarify what I'm trying to say. All right? So what we're doing here is we're adding a level of control. There's a specific variable that we are going to control because we know that that variable might impact the response. For example, women and men tend to respond differently to different kinds of advertising. Researchers for a national marketing company would like to design an experiment to compare the effectiveness of 3 advertisements that have been created for the newest smartphone that's released next summer. Help design an experiment that has 300 volunteers, 120 men, 180 women. Why might a randomized block design be preferred over a completely randomized design? Well, here's your answer right here. We know that women and men respond to different kinds of advertising. Okay? This is a fact. All right? So, there may be certain types of ads that are more appealing to men and certain type of ads that are more appealing to women. So what we do is we block them. So we take our 300 volunteers and we block them into 2 groups. Now, blocking is not done randomly. Blocking means you go here, you go here. Okay? This is done on purpose. 120 men and 180 women. Now, researchers for national marketing would like to design an experiment to compare the effectiveness of 3 different advertisements. So let's say, however you're going to do this, you're going to randomly assign them, let's say 40, 40, and 40 to advertisement A, advertisement B, and advertisement C. For the women, you're going to do the same thing. You're going to randomly assign them 60, 60, and 60 to advertisement A, advertisement B, and advertisement C. So what you're doing is you're saying, okay, we're going to isolate the men, and we're going to split them into groups of 40, and we're going to show each group of 40 a specific ad. And we're going to have them, let's say at the end, you're going to fill out like a 5 or 10 question questionnaire based upon when they saw, what did you like about the ad? What did you not like about the ad? On a scale of 1 to 5, how likely are you to buy this product based upon the ad that you saw? So women and men are going to see the same ads. But the question is, are they going to respond differently? So in a block design, when you compare, you only compare within the block. Compare responses to ads. Okay? And what happens here, let me finish this up before I speak here. Compare responses to ads. What the blocking allows you to do here is to say, all right, here's what we determined. We determined that the men had the most positive response to advertisement A. So this is the ad that we're going to run on ESPN. We're going to run this on Spike TV. We're going to run this on certain websites, so it's going to pop up. We're going to run this on any TV station that has a male demographic aged 18 to 35. But then we also found that women had the most positive response to advertisement B. So this is the ad we're going to run on stations that have a very high female demographic between 18 and 35 or 45 or whatever. So the blocking allows you to do that, to come up with different conclusions. Because if you bring everything back together, let's say, because some people will do this, you bring everything back together, well then you're just kind of coming up with one specific ad, and you've kind of nullified why you blocked in the first place if you bring everything back with each other. So by blocking them right off the bat, it allows you to come to a more specific conclusion. A more specific conclusion can be drawn with blocking. And I said, go back up to the top real quick. All right, when I said add control by isolating the blocking variable, we're isolating the variable of gender, and we're going to see how the treatments work within each of those categories of male and female. All right? All right, so now the homework is very similar to this, so take about 10-15 minutes and complete the homework and submit your work. Thanks, guys.